Welcome. If anyone can actually see me, my name's Mark Leckie, and I'm the kind of New South Wales ASEG president, and I'm your host for this webinar. This is really weird because I cannot see anyone except the speaker, Simon. It's quite strange. So I thought I'd run through a bit of housekeeping first, and then leave it to the main reason for the webinar, Simon. Right, first of all, just thank our corporate members, all those names there. They do great service to the society, funding the research projects and various things to do with the head office. Closer to home, the various branch sponsors, specifically in our case, New South Wales, GBG Australia. We are most grateful for them to fund our meetings, Zoom or not. Now, housekeeping. So up until half an hour ago, I had a slide which was less messy, but if you wish to ask a question, the Q&A button down here, if you click on that, it'll pipe in and you're able to type a message, and that should end up with both Simon and I being able to see it. Already the world is unmuted for you and there's no video because it's a webinar system, but if you have to type a question, please do in there. And we'll deal with all the questions at the end of Simon's talk. Just on the New South Wales side of things, we awarded one student scholarship. Normally we'd have the student front to the members at the rugby club, but Tom from the Union New South Wales on a project to do with machine learning of EM and gamma ray. Either we'll have Tom talking to an audience or have a Zoom audience later in the year to tell us how his project is going along. So well done, Tom. Future talks. Next week, I can see Peter Betts. Further in the future, Dave Annetts, and further in the future for New South Wales, Claire Mallard, who are giving various talks. Unknown if they're Zoom or in meeting talks. I'm guessing some of those will definitely be Zoom. I'm to advertise keeping in touch at this stage. There are our email newsletters, which are always a good read. Various website, Facebook if you're into that, Twitter if you're into that, LinkedIn if you're into that, and our YouTube videos. So the Simon's talk today will be made into a YouTube video. So for those who miss it, they'll be able to watch it accordingly. I don't think there's anything else. All right, I might let Simon share the screen, and then I might give him a quick introduction. All right, so while Simon's doing that, Simon Williams, he's the director and I'll say chief geophysicist at GBG Australia. When I did a brief Google of him, I'd found he'd been working for GBG for 20 years or so. Is that correct, Simon?
That is correct, and prior to that, with GHD and Aegis.
Yeah, and so he's been in the industry quite a long time, and he kindly agreed to give a talk on one of the things that interests him, and that was to do with using geophysics on a various dredging site in a park in Darwin. Without that, I think I'll pass over to Simon. They're all yours, Simon.
No worries.
I might remove my face from the picture for you.
Welcome, one and all. This is a speech or a presentation I actually gave to a conference on international classification of sites in 2016 in the Gold Coast. It was predominantly for geotechnical engineers, and it's based around a project that we undertook in Darwin for a as yet to be built marine industry park. It was basically preliminary characterization of the marine site, basically the channels and port areas that were going to be dug. This was undertaken in collaboration with Douglas and Partners, and also Landcore, who were the client. So, quick outline of the program for the talk. So, it will be introduction, quick discussion of the local geology, field work that was undertaken, the output, summary, and acknowledgements. I don't know why it's gone. Doesn't matter, I can't see too much of my full screen at the moment. So I don't know why that is, but I can't see any questions at the moment. So if you can leave them to the end, I'll see if I can find them then. Okay, so introduction to the site. So it's in Darwin Port, in the to the sort of southeast of Darwin, near the East Arm section, as you can see over here where the square is. East Arm is over here. That's the one that's currently used as a reasonable sized port. And this is the new construction. South of this, which you can't see here, but is in here, is the INPEX gas plant, which is running along here, pretty much directly opposite where they want to build the marine park. The reason for the marine industry park is that Darwin was looking at itself as possibly a service hub for the gas and oil industry that is sort of going to be happening in the Timor Sea. So it really wanted to base itself around the Singapore model and create an area where work and so on could be done on boats and vessels, loading and unloading of supplies, etc. Currently, this area is all mangrove swamps around here. There's a boat ramp in here. And a lot of this is exposed at low tide. So it's 148 hectares of development, 85 lots onshore, and a 3.7 kilometre long by 80 metre wide access channel, along with wharf frontage and turning points for vessels. This is a proposed development overlaying a bathymetry map. This was put out to the public to show them what was being done. And this is sort of a view from the boat ramp looking across towards the INPEX gas site, which is over here. You can see mangrove swamps in here already. Basically, there's two proposed dredging regimes. The first one would be to a negative 3.4 metres below lowest astronomical tide, LAT. And the next one would be 6.2 metres below LAT. These were obviously for different sized vessels as the park, the marine industrial park, expands. So they wouldn't all be done at the same time. Again, it just gives you an overview of the site with the boat ramp going in. Catalina Island is here. It's called Catalina Island because to the right over here is a Catalina base from the Second World War, and they used to fly in here and then go up onto the ramp over here. It's just next to the East Arm Wall. So local geology consists of marine alluvium, silts and clays, colluvial sand, silts, clays, coastal sand, coral shells. And these may be underlain by lateritic soils, old paleo soils. And these are generally underlain in turn by rocks of the Burrell Creek Formation, BCF. Or the soils of the Quaternary age may be directly underlain by the BCF. The BCF is basically called the Finnis River Group, comprises of subvertically bedded siltstones and sandstones, metasediments basically, quartz sandstone interbeds and frequent quartz veins, which can be very thick, up to 2 meters, along with minor quartz pebble conglomerates. The subvertical, in fact, they're pretty close to vertical. They stand around about 75 to 80 degrees. So not fully vertical at 90, but just off it. At low tide, you can often see up there what look like shark's teeth sticking out of the ground, and that's that's the bedrock bedding planes that are sticking vertically out of the mud. Some major site considerations considered for a marine project. The biggest one being is a tidal variation daily of between 6 to 8 meters, which meant much of the northern extent of the site was exposed at low tide. There was a lot of mangrove swamp in the northern extent of the site around where the port was going to be, which basically limited intertidal zone information. There's also marine heritage sites in the proposed dredge areas based on the Second World War, possible sunken vessels, aircraft, etc. Also the likelihood of unexploded ordnance possibility of it at least, from Japanese air raids, more as a result of the planes dropping bombs on the way out from Darwin that they didn't drop on Darwin, or trying to hit vessels or the Catalina base as they left the area. Seabed variation as well, from exposed rock to estuarine muds and clays. And some of the things you don't expect, or maybe you should expect in the Northern Territories, but you never think you're going to see. This was pulled out on the second day we're on site. It's a 2.5 metre crocodile. National Parks and Wildlife took that from a trap. They have something like, I think 80 traps around Darwin Harbour. And I think this was a record year for them. They pulled out over 200 crocodiles in the year, and at least 6 while we were on site. So wandering around mangroves in your shorts in mud is probably not the best idea. So, field work that we undertook: 183 line kilometres of multi-beam bathymetry. This was undertaken by a subcontractor, Astute Surveying, using an array. I can't remember what it was actually. It's not, but bathymetry is not my main thing. 147 kilometres of side-scan sonar. That's to provide full seabed coverage of the proposed dredge areas. That was undertaken with an EdgeTech system. The side-scan sonar was undertaken because it has a higher resolution than the multi-beam, basically because of possible magnetic targets, and also just to get a better handle on the classification of the seabed. 191 kilometres of, or line kilometres of horizontal magnetic radiometry profiling in the proposed dredge area for UXO and other significant debris. 111 kilometres of marine seismic reflection, sub-bottom profiling as it's called. It's basically a single beam seismic reflection system, basically looking for the interface with bedrock. And then 136 line kilometres of continuous seismic refraction profiling, which was used to provide an assessment of the hardness of the bedrock materials to be dredged. Along with that, 20 vibro core locations offshore and 40 test pits and boreholes on the land and in the mangroves. So let's get into the results. So first thing was the bathymetry. This is just a base contour model. Contours are at every 2 meters, I believe. The color gradient is in 1 meter intervals, but basically everything from here northwards was exposed at low tide. So all of this area all came out at low tide because that's a 0 there, and so it's all above. Varies in depth between obviously higher than 0 to around about 16, 17 meters. This straight edge here is the drop into a 17 meter deep access channel for the LNG ships for the INPEX port. This is this particular thing they didn't know existed here. They thought it was much further south. And it's one of the things that while we were on site, we were able to process this very quickly, this data, and we saw this and basically said, went to the client and said, there is actually a deep channel for the INPEX site at the bottom of your north-south access route. So you can pretty much remove, if you can get an agreement with INPEX to access that channel, you could remove the requirement for your east-west channel and therefore cut back on quite an extensive amount of engineering works. So as I said here, found this. They were quite interested in that, and I know they were pursuing it to see what they could come across. So we then undertook magnetics. This was a very dense grid. Lot of, because of the requirement of a UXO, we needed to get as close to 100% coverage as possible. Obviously in the deeper areas, the areas down here, we discussed with the client what to do, and they were not so worried about this particular area because a lot of it's below dredging depth, but certainly up here, a lot of dredged material is going to have to come out. So they wanted to actually check what was around. We're using an 882 geometrics, that should be, not geonics system, as a gradiometer, 1.5 meters apart, altimeter on it. We were towing it roughly, well, up in this place, probably 1 meter to 2 meters above sea level, but when we got down here, maybe 3 to 4 meters above sea level. Pretty much here, we were towing it hung from a float behind the boat, and we'd set a depth on a line, collect the lines as the tide went down. We'd be bringing it closer to the float until we couldn't actually tow it anymore. Then we'd move to deeper water, and then we'd come back here for the next high tide. This was the results. As you can see, an awful lot of targets, especially in the area where they're going to dredge quite a lot. Again, we went back to the client pretty much whilst we were on site, processed this overnight. Sections went back to the client and discussed it with them. Their opinion was that most of these would turn out, if not all of them, to be lateritic nodules. They'd had the same thing done for the Innerpex site and investigated 200 odd targets found in that site, and there wasn't a single bomb found. They were all laterite nodules where lateritic material had basically washed out the streams and then conglomerated together to produce a target that might be the size of sort of 2 or 3 foot in length by sort of like 8 to 10 inches or even a foot in diameter. These targets were dived on by recovery divers to see what was there. They did a few of these, especially in the areas, I don't know where in this area here, where there's a lot of strong targets. Again, it was all lateritic deposits. So they pretty much decided that they wouldn't spend vast quantities of money investigating these until later in the day, later in this possible project. There's another target in here, which is related to a heritage site, and I'll show you that in a minute from the sonar. So, again, we were able to categorise areas and localise those areas where there were many targets that we believed were of sufficient size. Brief overview of what I've just said, basically. So, into the side scan sonar. So this is actually a full mosaic of the site. It's because it's zoomed out quite a bit, you can't see an awful lot, but there's some paleosystem channels running through the muds here, which obviously become exposed during low tide, and so the creeks that are up here, they run into the mud and wash it out, and then when the sea comes back in, they sit at the bottom, and you can see where the actual creeks are coming out into this area. There is a large area of marine sand dunes here, sand waves. This is quite a large mound of sand that's sitting here, and there's obviously sand waves in there. There's another bunch of sand waves in here. Most of this has got rock on the bottom, and there's a little bit of rock in here as well, an exposed rock, and there's some exposed sawtooth rocks up here in bits and pieces. This is some close-ups. So these are the sand waves. This is exposed rock. As I was saying, it comes up like teeth. So you can see these shadows off the back, so it tells you how variable they are in height. That's pinnacles of hard material sticking out through the muds. This is a creek bed in the mud. That's when it's exposed at low tide, the water cuts through there. This is an old wreck that's sitting on the bottom. And this is actually from the side scan backscatter data combined with the sonar, which actually makes it stand out a bit better, but it's actually a Catalina flying boat. So it's a Second World War heritage site. And there's a wing over here, and there's a cockpit there, another wing here, and bits of the fuselage in here. There's probably an engine sitting out here. This actually turned out to be right in the middle of the channel they want to excavate. So I'm unsure as to how they were going to deal with that in terms of its heritage being a war grave. Well, I don't actually know if it's a war grave. I don't actually know if anyone died in it because it was actually just moored in the water when it got bombed. So this sort of gives you a bit of an overview of some of the targets we were pulling out. This is mangrove here. You can see these are root systems as well. The wrecks, which were all located up in this area and some over in here, were mostly due to Cyclone Tracy back in the 70s, which after smashing a lot of boats and completely sort of wrecking them and having them just floating or even on the seabed, the way the currents run in the port, they move them all into this area, and then now a lot of them are just stuck in here. There's an awful lot of rubbish from Cyclone Tracy sitting in this particular area. So this is a full view sort of classification of the areas. It's a conglomerate of basically the vibrocore information along with the sonar information on the seabed, so classified sort of the marine materials, and also there's some areas of strong side-scan sonar contacts and other bits and pieces on here. This were provided in an A0 and A1 and also electronic versions so that the client could actually see what was there. They've actually got this on one of their walls in their land Development Corporation's building there. So we found 112 targets on the seabed, could be potential hazards. Help classify the sediments, and as I said, there's wreckage from Cyclone Tracy and Second World War in the area. So sub-bottom profiling, again, very high level of profiling, very close lines, roughly, I think they were 25 meters apart, the longitudinal ones in this area, further apart here, 50 meters, I believe, here, because a lot of this is not requiring actual profiling with a dredge, because it's 17 meters or more, and the bedrock is actually sitting on the seabed. So for those of you who don't know what single channel seismic reflection is, basically we have a sound source, which in this case was a boomer, which is basically a plate, generally an electromagnetic plate. So you have a large pulse of energy. In basically when we were operating with 500 joules, it sends that pulse from a capacitor bank, which is this on the vessel, to the boomer. The boomer plate goes pop, and the source, the energy goes down to into the water through the sediment, reflects back, and is picked up by a streamer hydrophone, either following the source or adjacent to the source, parallel to it. Normally, it will consist of between 8 and 20 hydrophones, and they're all linked in series to give you one record. This is it being towed behind the vessel. It's on a catamaran. This is the source on a catamaran. This is the kind of information we got back. This is actually from the channel. There's the two samples here are from this channel. So the surface is here. The start pulse is here. The top of the water is here. This is the distance between the pulse and the actual eel. So it's about 2 meters, 2.5 or something. And then this is looking down into the water. Top of sand, in this case, it's going over the top of that large block of sand that you saw with the sand waves on it, and then dropping into the IMPEX channel. Bedrock is down here, sitting below the sand. And then within the sand, you can see bedding planes coming down through here. There's some variation of material through here. It gets a little coarser, and you can see there's a curve. There's probably an area of gravels or coarser material, like I said, gravels or maybe even larger pebbles through this area underneath the sands. The actual vibrocore that went in here didn't get that much penetration. I think it was like 4 or 5 meters at most, and it came up with sandy clays or clayey sands, whichever way you call it. I know there is a difference, percentage to percentage, but I can't remember which one it was. That's the reason why the sand holds the waveform, generally because it's got the finer material in there to bind it together. And this is over the more muddy areas at the top of the site where the mangroves are. So this is actually the seabed, very shallow here, and you're beginning to lose resolution at that point. The surface of the muds is here. The bedrock is down here, and we're getting this interesting flat horizon, which when they bored into this, turned out to be lateritic paleosoils. It's been cut through at this point by a channel at some point because the bedrock's coming right up into it, and here it just disappears completely. The bedrock is sitting directly underneath the muds. So basically, this is a contour map of the total bedrock topography. So this is again relative to depth below LAT. So again, here you can see that actually the rock is quite close to surface, exposed, or it will be under a very thin layer of mud and exposed at low tide. And as you get down further into the site, you can see it increases in depth to out here it's at 20 odd meters below. Here it's 15 to 20 meters area. So if we go over here and we look at the cut off at negative 6.2 meter dredge depth, so we've taken that information and basically cut a line through it and removed everything that was below 6.2 meters. These are the areas of rock, the maximum extent of bedrock that's going to have to be cut out from this site in order to get that dredge depth through those areas. Again, we had a fairly good understanding of this before we went into the next phase, which was the refraction, and it helped us actually cut down some of the data collection with the approval of the client, because they were spending money. They would be spending money collecting data in areas that didn't actually need to be dredged into. So this again is an overlay, basically showing differences of material, just classifying that material in a plan view format so that the client can get a full understanding of what's in the different parts. So this is all a sub-horizontal high amplitude reflection interface, basically the very stiff, hard materials. The very hard materials here, which is bedrock. These are areas of thick marine sediments, which would probably end up being dredged. So they're going to be dredging rock up here and mostly marine sediments down here. Again, quick conclusion of what we got with that. As the last thing is we provided evidence to the client that if they dredged directly into the impact channel at the south of the main access, this was a viable option with limited hard material within the area and possibly a source of construction material because it's nearly all sand. Okay, continuous marine refraction, the final method was used. This was asked for by the client at very high level of data collection, more than we've ever done on any site. Basically because previous dredging works had been, they based it on very limited information on rock hardness, and the dredging was always a problem. They'd end up having to change out dredging machinery and even blast material. So this was required at 25-meter centers in both directions, which is really a lot. We did most of the longitudinals at 25 through this area and through this area. We took out some of the transverses here because this area is completely devoid of any, the bottom of the sea is below the area they're going to actually dredge, so it's ridiculous collecting that data. There's also a couple of areas in here where we couldn't collect data because of obstructions on the seabed. Basically, you know, probably large bits of rock sticking up or even other things buried down there. The data collection was a mix of seabed towed array and surface towed array. The seabed was done in the deeper areas, the surface tow was done up here in the shallow areas. So just a few quick shots. This is us heading off to site. No equipment out. You can see there's an eel sitting here. This is an oil-filled 24, or I think it's 24, it might be 48 channel geophone. We had a compressor system down here with 2 tanks to act as reserves. That was powered by a generator over here. All of this lot was connected to geometric geode systems. And this is it out. So the array is out here. This is actually a surface towed part. The air gun's here. This is the air gun. There's a bolt system, 20 cubic inch. This is in the towed array vehicle. So it's a sled with floats on that we can pump up to lift it to the surface when we've finished. This whole unit weighs about 75 kilos, so it's pretty hard to get on board unless you can bring it up and float it. We basically did all of this data collection with just one offset because the surface tow, I think the maximum water depth we were working was 5 to 6 meters. And the bottom tow, it didn't really matter because we were bottom towing. So we basically set it to the depth we wanted to look below the seabed, which was around about 10 to 15 meters maximum. So beyond there, beyond the dredge depth required. Right, as you can imagine, with that amount of profiling with refraction is a lot of record. In fact, 14,000 shot records. We were shooting at 10-meter intervals along each profile line or better. 10 meters was the maximum we did. Each profile data set, we actually had to calculate the position of the shot in the geophones, and these were corrected in basically a program written in Excel or MATLAB by Pete Eccleston in our Perth office. And that system automated basically the position, the shot position and the geophone position for every shot. It's obviously corrected, and then first break arrival times were picked. Because the records were actually very clean, with clear refractors, obviously because the rock is so hard, generally, the process was able to be semi-automated. So that cut down a lot of time. We could go through a lot of picks and then just sweep through them and correct them if we felt that they'd lost track of where the break was. This whole data set was then exported to Tomo Plus modeling software to create velocity models. The reason for using GeoTomo is that not only can we look at 2D, but we can actually create a 3-dimensional model of the area. What we wanted to do was characterize the proposed dredge volume. So basically look at the entire site, creating velocity models from the initial data set in both directions, so that you're constraining your anisotropy, looking at neighboring lines and also the tie lines across. We took out originally, the first thing we did was take out 2D velocity models and look at these with the tie lines and make sure they had matching intersecting points, and calibrate them against the vibrocore data that we had, and also the sub-bottom profiling or seismic reflection data, see how close we were in terms of the velocity layers that we were getting back from the modeling. The sections indicated a relatively low velocity surface material, muds and sands, etc. Obviously 1600 to 1900 meters per second. These were draped over zones of higher velocity material, comprising subvertical velocity blocks. This pattern appeared consistent with the expected geology in the area. I'll show you in the next slide. So this is a line that's in red here, running east-west, and we're getting the lower materials over these area of higher velocity material with these peaks in it, which comprise of very high velocity material, and they're all sort of constrained their own little peak, which matches the geology of there being sort of near vertical bedded hard materials of such as the quartz within the area, quartz beds that are 2 meters thick, plus the metasediments themselves varied in hardness too. The other thing was that because of the vertical bedding, the system is known as being quite tight. You can dredge it quite well in a north-south direction because that's the predominant direction along the beds. But in the east-west direction, you're running against the beds. So you go through a soft bed and hit a hard bed, then a soft bed, then a hard bed, which is pretty much what these are showing. So the next thing we did was create a full volume, what we call 4-dimensional, so X, Y, and Z, and a velocity model. And this was produced by recursive inversion, leading to velocity values for each cell on a 3D grid covering the investigation area. And these were done to depths exceeding the proposed ultimate dredge depth. Using this, we were able to create depth slicing and extracting the velocities along a set depth. We could then stack the maps to demonstrate aerial and vertical distribution velocities for dredgeability. This bit was done in conjunction with Douglas and partners, who obviously are geotechnical engineers, and they can assess how dredgeable this material would be, and pick a velocity that they can then use to define areas that would probably need blasting. So these are 2 slices through that velocity model, the block basically. So it's a -3 meter slice, and you can see here the areas. The highest velocities being reds, up in the 3000s. Seen running through here, and a couple of little blobs out here. Going to the lower velocities, which are the blues. Obviously, when we get to 6 meters depth, we're getting a lot more rock and a lot more higher velocity area. So through here, there's a couple of areas. See, they're predominantly going in this, extending out here into this area. Blobs through here and here, a little bit of rock down here. So these were taken by Douglas and partners, and they basically looked at a velocity of about 2,300 meters per second. So they used that velocity based on correlations with others in adjacent areas of East Arm. As I said before, they had reported dredging difficulties, what they call shudder and ladder bounce on the dredging systems when they hit very hard material. So they can't actually cut through it, or they break the dredging teeth. So this was considered a velocity that was indicative of the need of rock blasting. And so the main reason of this difficulty in dredging is the subvertical layered rock material containing thick quartz veins, and the tightness of the rock in the subvertical position. As dredging along the bedding planes is fine, but across them is very difficult. So Douglas and partners basically took our information, and then they took all the stacks for the different depths, and then they created a plan view outlining the areas that are going to need blasting at different depths. So the green spots are little bits of rock that would need to be taken out if you just dredge to 0 meters LAT in an area that is plus 2 to 3 meters LAT. The red is the next, which is -3 meters. So these areas have obviously expanded a bit. And then the purple is if you're going to dredge to 6 meters or slightly more. So as you can see, you can get an idea of the extent of the area that's going to need to be blasted. And we can also volumize that because we know how deep it is below the bathymetry. So in conclusion, the geophysical investigation covered a very large area for a very sort of reasonable cost, I would say, in terms of the amount of information they got back for preliminary characterization, limited the amount of actual boreholes that they needed to do. it matched in very well with the limited vibro cores that they did, and some of the historical information they already had. So the client was actually very happy. We were also able to provide some targeted information on site by good use of time and looking at the data while we were collecting it and making decisions in conjunction with the client and Douglas and partners, sitting down in meetings with them and basically changing the scope of the survey on the fly, generally to save the client money. In the long run, it might have meant that we needed to collect a little bit more data in one area and less in another. There was also, as I said, a very dense grid of seismic refraction profiles, probably more than certainly more than we collected before this project, and we have not collected as much since this project. Most sites we'd be lucky to do 3 or 4 parallel profiles with a few cross lines. As I said, this particular one enabled us to create a very detailed model of the subsurface rock conditions and hardness so that potential dredging methods could be evaluated by Douglas. Finally, as I said, the potential channel alignment confirms that experience based in the field assessment of site conditions and collaborative relationship with the consultant and the client led to valuable outcomes, i.e. if they can set up an agreement with INPEX, then they could literally half the cost of their dredging channels because they don't need the east-west. Just like to acknowledge the collaborative nature of working arrangement between Douglas and ourselves, and also the Land Development Corporation, and for the corporation's permission to publish this paper. Thank you very much.
Thank you, Simon.
I have one question up here at the moment. Let me click on it and see what it says. All right, so the frequency of the source, with it being an air gun, was generally between 75 hertz and about 2000 kilohertz. The main frequency of response is around about 150 hertz to probably 150 hertz to 200 hertz. The actual hydrophones, they respond between 1 and 1000 hertz. Now, what else have we got here? What is the velocity entropy at the 2003 cutoff level, presumably, and a long strike cutoff velocity? How did you create a 3D velocity model in an isotropic rock? A long strike velocity model, a cross strike velocity model, geometric average velocity model. Geez. Jeff, I'm going to have to come back to you on that. Pete was involved mostly, Pete Eccleston, who's senior geo in Perth. It's 4 years since we did this project, so he's the person who was most involved in looking at the refraction, and I would need to take that up with him. Are you able to image lateritic layer overlying the older metasediments of the deeper bedrock succession in the refraction data? The answer is no. It didn't really have a very different velocity. It did show up as you say, in the reflection data, but the reflection data is generally collecting a much higher frequency, so it has a better resolution in terms of looking at smaller layer thicknesses. I think in that reflection, the layer is only 1 meter to 1.5 meters thick, so it's going to have a real problem showing up in the refraction data. Any other environmental considerations other than crocodiles? Obviously, the heritage issues. We had to avoid the Catalina that was on the seabed, so we couldn't tow the array on the seabed at those points. We knew where it was based on the sonar and the bathymetry. So that target was set up in our navigation system before we started the refraction, and we had to avoid that area. There was also a few other target areas that we had to avoid because of such considerations. Also, there's a couple of islands, Catalina Island being one, and there's also another little island which are actually Aboriginal reserves, so we couldn't run too close to those. I think, again, we had to sort of stop our lines short in some of those areas. In terms of whales and dolphins, the EPBC Act, when we did this, was a consideration. They had got exemption from it. There are, as far as I know, there are no whales within this area, but certainly we didn't see any while we were there. We did see dolphins. They're not part of the EPBC Act. We did actually shut down our gun if they closed within 500 meters of the air gun. But there was actually no requirement for us to do this. It was just something that we felt that we ought to do. Other than that, that was pretty much the considerations we had to take into account. The tides vary because of the shape of the harbour, which is sort of like a funnel, and also because of where it sits in the latitude. There's a large tidal variation because of the pull of the moon in this particular area. It's the same latitude if you come across Australia to Gladstone, and that part of Queensland has the same stroke, very similar tidal variation, 6 to 8 meters. The impact it had was in timing. Basically, we had anything, probably a 3 to 4 hour window in which to do work in those shallow areas, because the tide ran out and you had to obviously follow it. So because the area was so big and so different, there's so much variation in depth of water, we could actually move around the site to collect data in other areas that we could access while the tide was low, and then go back to the high tide areas once we'd finished, once the water had come back. So in terms of time, it didn't really impact us too much. It was just very good and very careful planning with both ourselves and the local bathymetry operator and boat driver who knew the area very well, having lived there since Cyclone Tracy. And he was extremely helpful on site in allowing us to set stuff up and work the way we did. Were tidal corrections an issue? Actually, no, because the RTK system we have on board the boat was set for lowest astronomical tide. So we just do the corrections to everything based on the recording, the Z recording at the time we were collecting it. This was done by the local surveyor we were using, so he knew exactly what we were doing. It saved us a lot of issues later on with obviously a 6 meter tidal movement. Regis, could you see the wrecks in reflection data? No, they certainly didn't show up. We didn't get anything that looked particularly vessel-like. I think it was, the frequencies again were too low. You might get a bit of bounce off the metal work, but they just didn't show up. Not really an imaging system for surface. Mike Smith, was any filtering or processing applied to the magnetometer data with the objective of discriminating the lateritic nodule accumulations from higher susceptible sources? The answer to that is we did do a little bit of filtering. We actually used the UXO software created. Well, it was created originally by the guys out at St Mary's here. I think Tim Pippett was one of them. I can't remember what it was called, but it was used by Backtech here in Australia, and we actually at the time were contract geophysicists at Backtech, and so we then used their software to actually process this data specifically to try and discriminate targets that would be the size of a bomb. Unfortunately, the lateritic nodules were also pretty much the same size as a bomb and had the same kind of response. And as was saying, that Lancore had the same problem with INPEX channel, and they spent a vast amount of money doing diver inspections for that site and found no UXO. So they were fairly sort of ambivalent about doing further work on this, as it was very, very similar. The answer to Regis, he said, did you need to correct any data for swell to get down to a meter resolution? The answer was no. The harbour is so well protected that there is really no swell in it. The only thing we do get is a bit of wind-related fetch chop, which tends to be 300 to 500 millimeters at most, and that's mainly when the water gets up to, when the wind gets up to about 20 to 22 kilometers an hour. We were very lucky. We had very good weather while we were there for nearly all of the work that we did. Given Robert Houston, given during the last ice age and previous ones, the sea level was approximately 130 meters below current levels, is there any indications of that history and its surface ground nature? Not that we saw. We were only looking to a depth of, I think it was 15 to 20, about 15 meters below seabed with the refraction. And with the reflection, once we hit the bedrock, we got very little information beyond that. In terms of paleo channels and so on, could not really see any indication of paleo channels within the bedrock. Tavis. Good buddy Tavis. What applications other than dredging have you used these near-surface marine geophysical methods for? So we've done work for HDD bores, cable connections from offshore cables such as into international ISDN cables for the internet, and also for river crossings, for pipelines and cable routes, sewer outlets, desal plants. So it's fairly well-known methods for doing this kind of information gathering. It is obviously preliminary work. It's always done up the front end of geotechnical investigations because it's cost effective as opposed to putting a drill rig in where you start having to pay large amounts of money to put drill rigs on barges or mobilize an actual jack-up platform from some locality. Obviously, you're only getting a small point source of information on a very large project that's 3,700 meters in length and 80 to 100 meters wide. We actually collected over an area that was 200 meters wide because the client required that. Dave King. When towing refraction spread above seabed, what method did you use to correct for the water thickness? Well, basically, we utilised, we created the model and then we utilised the bathymetry to remove the water from the final data. So we knew at the time we had bathymetry that was corrected to LAT, and so we knew the depth and position of where we were collecting the refraction information from. So we're actually able to just remove the water layer, treating it as a layer, and removing that from the data. Obviously, as a layer, we knew what velocity it should be. I think it was 1536 meters per second. So we're able to actually take that away from the block, and then everything below that was considered to be either water-filled sediments, and they would get, obviously progressively faster as the water gets squeezed out with depth, and then obviously the bedrock's below that. So sharp change in velocities going into the bedrock. That's all the questions I've got here at the moment.
There's one in chat, Simon, from Ned Stoltz. He asked quite early on, what is the fold of the seismic? I think he was talking about the single channel.
Yeah, it would be. The single channel, there isn't a fold on that because it is only one channel. The refraction, we don't really look at fold for that. Okay.
Right, now you've gained one last question.
Where's that? Did you encounter any issues with older buried mangrove swamps causing the localized biogenic gas blanking out seismic data? Funnily enough, no. We've had no gas issues on this site. I was expecting them, especially in the single channel data, but didn't seem to be the case. The biggest issue was just the lack of water up near the mangroves, because obviously it's above LAT. So, you know, after at the most we got was 4 or 5 meters of water, and we'd collect data, and occasionally we'd lose resolution because we were getting down to 2 meters, and the system doesn't work once you get water at depth of 2 meters. The energy just bounces around between the seabed and the surface.
All right, I think I'll bring it to a close there. There are many people texting in, nice talk, great talk, etc. On behalf of the New South Wales ASEG, there's a bottle of wine which comes in and out with my backdrop. Thank you very much, Simon, for a very interesting talk. Everyone listening, Simon's talk will go on the YouTube channel at some stage. Thank you all. Thank you, Simon.
Thank you, mate. Cheers. Thanks all.